Thank you, everyone. So, today I'm going to present MagicDot, a hacker's magic show in which we'll see how much magic dots and spaces create in Windows. So, just a second, my clicker doesn't work. Now it does. Yeah, so this is me, Or Yair, so my first name is basically a condition. Um, I'm the security research team lead at SafeBreach. I have about 7 years of experience in security research. In my past, I researched some Linux embedded and Android environments. And for about 4 years now, my main focus lies in vulnerability research in the Windows operating system and third-party software that runs on it. So let's stop talking about me and see what we're going to discuss today. So we're going to start with an introduction of a known unfixed issue in Windows that is the base for this entire research. We'll then see the research goals that I defined for this research. Then we'll see the post-exploitation techniques and vulnerabilities that I found that are all based on this known issue. And we'll wrap it all up with CVEs, fixes, takeaways, and a link to the GitHub repository with all of the abilities and magic tricks that we'll see here today. So, as you all probably know, backwards compatibility is a key element in Windows. As the world's most popular desktop OS, Windows is trying to evolve while maintaining its already invested customer base by not breaking any feature or third-party software that they use. As a result, there must be some known issues that are left unfixed. And this is exactly what I encountered while I was researching something else. Basically, by accident, using a special API, the NT-API that we'll later discuss, I created a file. I wanted at least to create a file that is called a.txt, but I accidentally created a.txt dot. I immediately noticed the error, and so I created a.txt and then wanted to delete a.txt dot. Then, as a result, the thing that happened when I deleted a.txt dot is that a.txt was actually deleted instead. I deleted one file, and another file was deleted instead. It looked like pure magic. And so I decided to investigate the magic trick, the magic primitive, become a magician myself, and build my new hacker's magic show. So let's go into investigating this issue. Basically, when I read Microsoft's documentation, I saw something that I was very surprised about. And that was that Microsoft explicitly asked users to not end a file or a directory name with a dot or a space. But what do hackers do when someone tells them not to do something? Of course, they do exactly that. But before we are going to start playing with trailing dots and spaces, let's really understand what happens when this known issue occurs. So basically, when you are using Win32 API calls, most of the times they won't do the actual operations themselves. And as you probably know, they use underlying calls from the NT-API, which perform the actual operations, speak with the kernel, and everything. But when you provide path arguments to these Win32 API calls, you usually provide what's called a DOS path, which is the normal type of path that we are all normally using. Now, NT-API does not work with DOS paths. Instead, it should be given NT paths. So we see the bottom example here is an NT path, and the top is a DOS path. So that means that somewhere between the Win32 API call and the NT-API call, a conversion must occur. So the Win32 API call performs a conversion from DOS to NT path, and as far as my check goes, This conversion happens by the RTLP DOS path name to relative empty path name. And apparently, this converting function just removes trailing spaces and dots in the following format. So pretty much any trailing dot from any path element is removed during the conversion, and trailing spaces are removed only from the last path element. So here we have a few examples for that. We can see the top 4 examples have trailing dots and trailing spaces in the last path element. And we see that after the conversion, they are all removed. And in the bottom 2 examples, we can see that in the second path element, we have, in one example, a trailing dot, and in the other one, a trailing space. The trailing dot is removed during the conversion, but the trailing space is not, since it's not the last path element. If you want a deeper dive into types of paths in Windows and to know exactly how they're converted into empty paths, then I really recommend reading the blog post by James Forshaw from Google Project Zero. It's called The Definitive Guide on Win32 to Empty Path Conversion. It's really informative about these matters, so I really recommend it. But after I understood this magic primitive in Windows, it just immediately hit me that this could be just perfect for some rootkit magic. My assumption was that if I'll create paths that by intention have trailing dots and spaces in them, then I'll be able to manipulate what users on the system see. So we all know that the primary goal of a rootkit is usually to conceal malicious artifacts. But in order to understand how this rootkit would be different, let's briefly go over the most known and popular types of rootkits, which are user space and kernel space rootkits. So a kernel space rootkit, of course, runs in the kernel. It will usually hook APIs of the kernel, such as system calls. And when certain information is requested, then the hook of the rootkit will call the original function, remove the malicious artifacts, and return the information without the malicious artifacts that it wants to hide. Now, in order to run a kernel space rootkit, one would need to have administrator privileges and to handle mitigations, such as the driver signature enforcement policy, driver block list, HVCI, maybe patch guard as well. And for this reason, we barely see kernel rootkits in the wild anymore. And what we see more is user space rootkits. So this type of rootkit, of course, runs in user space. It does the exact same thing where it hooks API calls to remove malicious artifacts. But it does that by first injecting itself into processes in user space, and then it hooks the API calls in these processes. So in order to run such a rootkit, one would still need administrator privileges, because a user space rootkit would still want to hide itself from all users on the system, meaning it needs to inject itself into processes that run with administrator privileges. So it needs to have administrator privileges. But then a question comes up, and this question is, what happens if a certain attacker has managed to breach an endpoint, but does not have a way to escalate their privileges? So they won't be able to hide themselves? What if a certain attacker was able to breach a certain endpoint and is even able to escalate their privileges, but they just don't need it? Do attackers must have administrator privileges to hide themselves? These situations where attackers cannot escalate their privileges because maybe it's just a fully updated machine and the attacker has no vulnerabilities can happen, of course. And with that being said, I was not able to find any abilities that allow unprivileged users to hide themselves from all users on the system. So what I realized was that there could be a way to hide malicious artifacts without being a part of the chain of calls like any rootkit does, and without needing any special permissions. That is because this known issue already lies in the chain of calls that retrieve information. When someone retrieves information about a file, then it goes through this converting function. So basically, by creating paths that by intention are converted to other paths, which may exist or not, we can manipulate the things that all users see on the system, even when we are unprivileged users. So the first research goal for my research was updated to also not require any special permission, so I'll be able to create rootkit-like abilities without any privileges. The second research goal was much more simple, and that was pretty obvious: to prove that such unfixed known issues are indeed a serious security risk, and the easiest way to prove that would be by finding vulnerabilities that are caused due to this known issue. So, without further ado, let's see some rootkit magic with files and directories. The first and most obvious thing that we can do is to name a file or a folder with just dots and spaces, or just add trailing dots or spaces to the end of an existing file name. Once we do that, basically no one is able to take any file operation against this file or directory, because the trailing dots and spaces will be removed and the final path will reference a non-existent path. So if, for instance, we name a file blah blah dot dot dot, and there is no file that is called blah blah in that same directory, then no one can read that file, no one can write into it, no one can delete it, and that is true for directories as well. But we can take this even further. We can create a file that impersonates a different file. So let's say that there's already a benign file in a certain directory that is called benign, and we are interested in creating a file that has malicious content, but we don't want anyone to see it. So we can create in that same directory a file that is called benign.dot. Then any file operation that is taken against benign.dot will be redirected to the original benign file. And that is true for directories as well. So if, for instance, we create benign.dot and someone tries to read benign.dot, then they will be given back the content of the original benign file, and that is true for directories as well. If those were directories, then if we list the benign.dot directory, then we'll be given the files that are stored inside the benign directory. And that is true for any other file operations as well. Now, another backwards compatibility feature that we can use to empower our unprivileged rootkit-like abilities is called short names, aka 8.3 file names. Basically, these were just the default names back in very old versions of DOS and Windows. They're not the default one today, but we can still use them apparently, and just set an alternative name for any file or directory that we have on our file system. So let's see how we can leverage that. Let's say that we consider the situation of two files that are named with the same name, but one has trailing dots, a bit too suspicious. And we want to create two files with completely different names, but store malicious content in one of them, and then when someone tries to read it, then it will be redirected to a different file. What we can do, let's say in this scenario, we want to create a file with malicious content that impersonates to a.txt. So what we can do is to set the short name of the file a.txt to be LOL, for instance. Then if we create a malicious file that is named LOL.dot, then any file operation that is taken against LOL.dot will actually remove the trailing dot from LOL dot, finally referencing LOL. But what is LOL? LOL is actually a.txt. So any operation taken against LOL dot actually is taken against a.txt. And these short names, as far as my check goes, you cannot view them in any other way than just specifically running the command dir/x or using the very specific API that is meant for retrieving short names of files. So this is pretty much hidden as well. Finally, another way that we can leverage to hide our files and directories is just storing them in zip archives and adding trailing dots. Because of the fact that File Explorer has difficulties functioning with such problematic paths, then if you just name a file or a directory in a zip archive with a trailing dot, then when File Explorer lists this archive, it just doesn't show you this file that is present inside the zip archive. And when it's extracted, then it does not extract this file as well. So nobody will be able to know that the file or directory is there unless they use a different extractor. So we saw some nice magic tricks, but let's see how they all can be combined together to really to hide our malicious content in a stealthy way without any special permission. So in this demo, we'll see just a presumably normal directory called test that has a few files, 2 folders, and a zip archive inside. In the first part of the video, we'll see how Windows views their content through Notepad and CMD. And then in the second part, we'll see their actual content using Linux and WSL. So we can see the files in the directory. We print their content using the type command. We see that it's all just a textual content, normal content. And we have 2 directories with the file a.txt, dir1 and haha.dot. Then in the zip archive, we also had 1 file that is just a.txt. We can see that the content of the file is shown the same in Notepad and also inside the zip archive. And now let's see the same thing in WSL. So we're starting to print the content of the files using the cat command. And suddenly, these files has the textual content, malicious content in them. When we'll try to print the content of the a.txt file inside the directory haha.dot, it's actually not there. And instead, we have 5 executables inside. Now, when we extract the zip archive using WinRAR instead of File Explorer, then what we'll see is that there was actually 1 more file present inside that File Explorer just failed to show us. OK, so we did some magic tricks with files and directories. Let's move on to rootkit magic with processes. So the most obvious thing that we can do again is just to create a process that I call an untraceable process. So basically, what we'll do is to run an executable from a path like c windows dot, then blah, 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 blah.exe. What will happen as a result is that anyone who takes any file operation against the image path of this process that we ran is just redirected to a non-existent path at the real Windows directory. And there is no blah, blah directory inside the Windows directory. So no one can take any file operation against the image path of this process. And the software that lists processes, such as Task Manager and ProcExp, are not able to view any properties against this image path. But just like we could with files, also here we can create a situation where we impersonate a different process. So to do that, we'll run an executable from a path that when converted to empty path, then it really refers an existing and trusted executable. So in this case, we can, in this example, we can run a file from C Windows dot system32 svchost.exe. And then when anyone references this path, the trailing dot will be removed, referencing the real SVC host executable, meaning that, again, any file operation will be taken against it. And also, tools like Process Explorer and Task Manager will tell you that the image path of this process is verified and signed by Microsoft. Also, prefetch analysis tool will tell you and provide you information about the original trusted SVC host executable. So let's take a look at this ability. In here, we'll see how we are running Mimikatz with the MagicDot tool in a way that it impersonates SVC host. And later on, we'll use Process Explorer and Task Manager to view information about that process. So we see that we have the MagicDot tool and Mimikatz. We are asking MagicDot to run Mimikatz in a way that it impersonates SVC host. So we have Mimikatz up and running. Let's find it in Process Explorer. Click on it. We see that it tells us that it's the original path of the actual SVC host executable. And we click Verify. It tells us that this executable was created by Microsoft. Now we're looking for the same process in Task Manager. So we look for the same PID. We click Properties. Now let's see what we're seeing. So it tells us that it's located in the real system32 folder and that it's actually signed by Microsoft. And I hope you all know that Mimikatz is not signed by Microsoft. Thank you. So as part of my journey for exploring bugs that are based on this known issue, I did some reverse engineering to Process Explorer as well as many other things. And I did not find any more issues in Process Explorer that are based on this single known issue, but I did find a nice way to empower my unprivileged rootkit abilities. So this would be a nice addition. Let's look at that. Basically, while I went through Process Explorer's code, I saw this line of code that copies the process name into a wide string buffer and limits the final length for the wide string buffer to be 256 characters. That makes sense because process names are determined by their executable names, and NTFS limits the maximum length for a file name to be 255 characters. So we're safe here. But then 2 lines of code after that, there's a concatenation of the PID surrounded by parentheses into the same wide string buffer. So we can immediately see that given the fact that they still limit the final length for the buffer to be 256, we can go over this limitation. But how does that help us? I mean, this is a safe C runtime function, right? WCS_cat_s. Safe C runtime functions are meant to protect us, right? So safe C runtime functions are really a more secure version of C runtime functions because they add a few extra security checks. But what happens when these security checks go wrong? Basically, they invoke an error handler. Just like we can see in this case, this invokes the invalid parameter error handler. The invalid parameter error handler calls the user-assigned invalid parameter handler, but if there is no one assigned by the user, it just calls invoke Watson, which closes the application and generates a mini dump, like we can see here. If there is no handler, it calls invoke Watson. So what does this actually mean? It means that with the privileges of any user, we don't need any special user to perform that. We can just run a process with a very long name that will cause any instance of Process Explorer that runs in any context, even administrators, to just immediately close and to not be able to run again as long as this process with a very long name is running. So this is nice to empower their rootkit-like abilities in order to prevent anyone from using Process Explorer to see your process. But I think that there's another mini lesson that we can learn from this scenario, and that is that safe C runtime functions are not as safe as you might think. It's not right to just count on safe C runtime functions to do the validations for you. Basically, in this case, the risk was just pivoted from a buffer overflow to a denial of service security risk, which is indeed less risky, but that is still a vulnerability. So make sure you do the proper validations before you call anything, even if it's a safe C runtime function. So let's take a look at this vulnerability. Basically, we'll just using a process using an executable that I created that uses the NT API, because this is the only way that you can do that. We are going to run an executable with a very long name, and this will cause Process Explorer to just close and not be able to run again. So we open CMD, run my executable that runs the executable with the very long name. And Process Explorer is closed immediately and is not able to run again. And that is true for all users on the system. Great. So far, we saw some nice magic tricks. But now we are moving on to some real magic. And in the case of hackers, real magic is vulnerabilities. So without further ado, let's see the first magic act for this show, in which I'm going to show you how I'm going to make a folder completely disappear. So basically, our target folder will be the C demo folder. I do not have permissions to do anything to the C demo folder. I do not have permission to do anything to its files. However, I do have permissions to create a folder inside the demo folder. What I'm doing is that I'm creating a folder called ... and then I'm placing a space at the end, and I'm placing just a file inside. Now, to complete this magic act, I need an administrator volunteer, which will see this very strange-looking triple dot space directory, and will try to delete it because it does not know it. So let's see what happens when this occurs. The administrator goes into the demo folder, sees a strange-looking directory that was not there before and looks just like a bug or something. So they try to delete it, and as a result, the entire demo folder is just deleted instead. But what happened in here? So basically, the process that tries to delete the folder, the triple dot space folder in here, is File Explorer, of course. And when it wants to delete a certain folder, it starts with recursively listing all the files inside. So it lists the triple dot space directory, but listing the triple dot space directory just lists its parent directory, because when we refer to a path element that is made from only dots and spaces, it's completely removed, referring to the upper directory. So it continues listing the files, and it sees another non-existent triple dot space directory inside, so it tries to list it as well. And in this case, I know it's a bit confusing, but in this case, it does actually manage to list the right triple dot space directory. And that is because the last path element is removed just like we saw in the past example. But the one before it is not removed, because if you remember at the beginning of the talk, I mentioned that trailing spaces are removed only if they are a part of the last path element. So basically, the fact that we gave a name made only from dots and spaces but ended it with a space prevented an endless recursive loop listing all the files inside. Then when File Explorer finishes to list all the files, it finally list all the files and delete all the files inside, it finally deletes the parent directory. But the parent directory is triple dot space, right? So deleting C demo triple dot space is equal to deleting C demo because the entire last path element is removed. The second magic act for this magic show will be changing the memories of a shadow copy. More specifically, I'm going to show you how a shadow copy should remember a certain benign content about a directory located at C demo test, but actually I'm going to change its memories and cause this memory in the shadow copy to be a different content. So our target directory will be C demo test. I do not have permissions to change anything inside the test directory or do anything to it, but I do have permissions to create a folder next to it. So what I'm doing is that I'm duplicating the test directory. I'm leaving the same name, but I'm adding a trailing dot. Then I'm modifying the files inside the test space directory to be with the content that I want to write into the real target test directory. Then in order to complete this magic act, I need the administrator volunteer again to create a shadow copy of its test directory, and then in a later point in time to just restore this very same shadow copy. So let's take a look what happens in this scenario. So we see that we have two files inside the target test directory, a.txt and b.txt, and they both have the textual content innocent. Now the administrator creates a simple shadow copy. So the shadow copy is created, and then in a later point in time, the administrator wants to restore that very same content, so it should remain the textual content innocent. But let's see what happens in practice. So we print the content of the files inside the test directory, and it was actually changed to be the content malicious instead of innocent, even though we restored the version that should contain innocent. And now we reach the grand finale, the best magic act for this magic show, in which I'm going to show you how I'm able to hypnotize a remote computer to run my malicious code. More specifically, we're going to see how I'm able to craft an archive that when extracted on a remote machine, it will write a file to wherever I want on the disk. Windows actually has a great attack surface for such a vulnerability now, since last year, Microsoft added support for many new archive types that we've all been waiting for. Now, when I started the research about this vulnerability, I considered symbolic links to be a very good lead. Now, it's true that the victim would need to have the create symbolic links user right or developer mode turned on in order to create a symbolic link. However, I still consider that as a valid attack surface, as all extractors do support symbolic links, and developer mode is also a feature that is turned on many computers. So my initial thought, you know what, let's take it one step backwards. Actually, extractors do not see a major risk in allowing symbolic links. This is not like an optional feature or something that you need to turn on in the extractor. They do not consider it as a risk because the extractors do not allow the functionality of writing into the target of the symbolic link. They just allow the creation of a symbolic link, and this is not dangerous. However, we have our MagicDot magic. So what I thought was to maybe place two files in an archive, have them named the same, but place a trailing dot in one of them. Then, if I set the first file to be a symbolic link to wherever I want to write a file on the disk, and then set the second file to have the content that I want to write into the target of the symbolic link, then what I hope that will happen is that when the extractor extracts the first file, which is a symbolic link, then it will just be extracted successfully. The symbolic link will be created and point towards my target. And then when the second file will be extracted, then the trailing dot will actually be removed, and the extractor will accidentally open the already existed symbolic link and will write the content of the second file into its target. And again, this is at least what I hoped for. A secure behavior against such an attempt would be that the extractor will see that the first file was already extracted and will ask you whether you want to replace it or just not extract the second file. And this is exactly why the create file call that extracts files from an archive in this new extractor that Windows added uses the create new create disposition, the flag that you see in the fifth argument. So basically, this create disposition just affects the create file call to fail if the file that you are trying to open or create already exists. So this should lead to the scenario where this only creates new files. But there is a critical flag that is missing here, which is the open reparse point flags, which basically just tells the create file call that if this call references a symbolic link, then it should refer to the symbolic link itself as a file and not follow its target and refer to its target. So the fact that this flag is actually missing in here means that if we do call this exact call for a symbolic link with a target that does not exist, then this call will actually comply with this scenario and will actually create the target of the symbolic link. So that means that we can actually follow the original attack vector that I suggested, create an archive with two files inside. The first one should be a symbolic link that points to somewhere that does not exist. So for instance, this would be an executable in the startup folder. Then the second file will be the content of the executable that we want to create. Then when this archive is extracted, it will create the first symbolic link that points towards the non-existent executable in the startup folder. And when the second file is extracted, this action will create the target of the symbolic link and write the content of the second file into it, leading to our executable in the startup folder and to our code execution on a remote machine. So let's take a look at exactly that. In this demo, we'll see a tar.gzip archive extracted in the downloads folder, and then as a result, we'll see calculator created in the startup folder. So we extract it in the downloads folder, and we create an executable in the startup folder. So we extract the archive, and calculator was created in the startup folder as a result. Now we log out of the current user, log back in, and I guess you'll know what's going to happen. Calculator will run, and we managed to run our code on a remote machine. Thank you. So these were the magic acts for this magic show. We can now move on to some CVEs, responses, and fixes. So basically, Microsoft created these three CVEs for the RC in the extraction mechanism, the elevation of privilege using the shadow copy, and denial of service in Process Explorer. They were all fixed, of course. Regarding the deletion elevation of privilege, Microsoft did confirm the behavior, but decided that this does not meet their severity bar. Hence, they're not going to fix it. They said maybe in the future. and regarding all the other rootkit-like abilities that unprivileged users can run. They just identified that as post-exploitation techniques, and post-exploitation techniques are not getting fixed, just vulnerabilities are getting fixed by MSRC. So this was the status of fixes and CVEs, and this is the maybe most important slide of this talk, maybe for all talks in the world, and this is the takeaways. So basically, the most obvious takeaway and most important one that we can understand from this research is that known issues that are left unfixed are indeed, can be very dangerous and are serious security risks, even if you don't know the risks that are causing. So if you just see a known issue that you think that is okay and it's just a bug and it won't create any risk, don't ever assume that. You should treat that as like it can be very dangerous. Second, we also learned from this talk that malware can be hidden even without administrator privileges from all users. So even if you're an admin and you are positive that the malware that you are investigating does not have administrator privileges, it can still hide stuff from you without being a part of the chain of calls that retrieve information and without these admin privileges. Third, Microsoft chose to fix only the specific vulnerabilities that I found and not the actual root cause, which is the known issue in the conversion function that converts DOS paths to empty paths. So while these vulnerabilities are fixed, there might be more vulnerabilities to find. So I really encourage you to try and leverage this known issue to find more vulnerabilities before real attackers do. And lastly, an advice for developers would be that most Win32 API calls do support anti-paths as well as DOS paths. So by using anti-paths instead of DOS paths wherever you can make sure 100% that you are accessing the file that you intended to access and you are not being manipulated. So take this with you when you use paths. And basically, this was the talk. This is a link to the GitHub repository with the MagicDot tool that combines all of these abilities together. You can also scan the QR code. You are very welcome to contact me on my social media or email if you have any questions. And I'll also be here for any questions if you have them. Thank you very much, everyone.